In this video, we're going to learn about substitution. And substitution is a more formal approach to what we were learning in the last video. In the last video, we were looking at some function that we were doing the reverse chain rule. So we had something like f prime of g of x times g prime of x dx. And in the last video, what we did is we were trying to identify, what is my g of x, what is my f prime of x, what is my g prime of x. And if we could identify all of those, we were able to do the reverse chain rule. But what substitution does is it improves the process of the reverse chain rule. So let's, before we actually do a substitution, let's just review the method that we learned in the last class. So let's say that we were trying to integrate the square root of x squared plus x times 2x plus 1 dx. Well, what we did is we said, okay, let's try to identify what our inner function is. And what makes that easy to do is we say, okay, well, this looks like it's inside a function. It looks like it's inside the square root function. And in fact, its derivative is over here. So the derivative of x squared plus x is 2x plus 1. So we can say, let's g of x is x squared plus x. G prime of x is 2x plus 1. F prime of x is this, so is root x. So therefore, f of x, finding this antiderivative, is going to be x to the 3/2 times 2/3. So we know that this antiderivative, or the integral, will be f of g of x, because it's the anti-chain rule, where f is 2/3 of something to the 3/2, and that something is g of x. So x squared plus x. Just to be clear, that was to the 3/2. Okay, so this process works, but and some of you are going to stubbornly adhere to this process, even though I'm telling you what we're about to learn is a much better technique. So buy into this new technique. The new technique, substitution. Substitution. In substitution, we're going to let some function. We're going to let the function g of x equal u. And then we're going to find g prime of x. And if we think about that, taking the derivative of both sides, g prime of x written a little bit better. Let's write that as well, let's say g prime of x equals du dx. So I'm taking the derivative of both sides. And then instead of having our function be in terms of dx, we're going to have our function be in terms of du. And while this may seem like a lot of kind of strange steps right now, when we do an example in a second, it's going to make the integration incredibly easy. So let's look at an example of using substitution. And the key, the skill to develop is to figure out what to define as u. But for now, I'll give you some hints. So let's do that problem we just did. We have the integral of the square root of x squared plus x times 2x plus 1 dx. So typically, we're going to let our inner function be u. So we're going to say let u equal x squared plus x. Okay, so we substituted u. We did this. Now we're going to take the derivative. So we have du dx equals, well, take the derivative of this side, 2x plus 1. Notice that's showing up here. So we've done this. And now we need to find du. So du equals 2x plus 1 dx. Oh, nice. That's this. So now we can do the substitution. So we have the integral of the square root of x squared plus x, but that's u, times this whole underlined portion is just du. So it's just the integral of root u du. This integrates really easily. This is 2/3 u to the 3/2. If you can't see that, just as a reminder, we could think of this as u to the 1/2 plus c. Okay, and then the final step is to substitute back. So we don't want it in terms of u, we want it in terms of our variables x. So the integration becomes 2/3. What was u is now x squared plus x, because they're equal. We define them that way, raised to the 3/2 plus c. And while this may seem like a couple more steps, as problems become more and more sophisticated and challenging, the u substitution makes integration manageable in an otherwise unmanageable situation. Okay, so we're just going to look at a couple examples of doing u substitution. All right, so let's think about taking the integral of, in parentheses, 1 plus tan of 4x cubed times sec squared of 4x dx. All right, so this is a kind of an ugly integration problem, but some things that you should start noticing, start picking up. You know, we've got a sec squared and we've got a tan. So there's some, you know, the derivative of tan is sec squared. So that should start cluing in reverse chain rule. So what we should do is we're going to let u equal something. Let's let it equal the inside function. So let u equal 1 plus tan of 4x. And if that's the case, then du dx equals secant squared of 4x times 4. Because we have to use the chain rule, derivative of the inside. So we get du equals sec squared times 4x times 4 dx. Okay, well, slight minor alarm bells should be ringing because in terms of doing replacement, this has a 4, whereas this doesn't have a factor of 4. So what we need to do then is let's multiply both sides of this equation by 1/4. By doing that, that's going to cancel off, and we have sec squared 4x dx, which is exactly what we want. So now we can substitute. So we have the integral of u cubed times 1/4 du. Substituting this in for that, this in for here. A little bit of rewriting. Let's pull the 1/4 out in front. And now, you know, if we think about our original integration right there compared to our u substitution integration, it becomes significantly easier. So we get that this equals 1/4 times 1/4 u to the 4th plus c, where this is just the evaluation of the integral of u cubed, making sure that we have the plus c, always plus c. And now the last step is to substitute back in for u. So we get 1/16 times u to the fourth, where u is 1 plus tan of 4x raised to the fourth plus c, and voila, we are finished. Excellent. Okay, let's do another example. All right, this example is going to look a little bit different. So we're integrating a fraction. So we're going to have, let's see, t squared plus 4t over 2t plus 4 dt. And what we recognize is, the top is the derivative of the bottom. So our inner function is the bottom. So we're going to let u equal t squared plus 4t, and therefore du dt equals 2t plus 4, which is the top. So solving for du equals 2t plus 4 dt, which is exactly that. Therefore, we can rewrite this whole integral in a much simpler fashion as the integral of 1 over u du. And that, we remember, can integrate to ln of the absolute value of u plus c. And our last step, which we always remember to do, is to resubstitute. So ln of the absolute value, t squared plus 4t plus c. Nice. Okay. The next example is going to be a definite integral where we have limits of integration. In this example, when you have a definite integral, there is no need to resubstitute. Just change your limits to u. All right, what do we mean by that? So let's imagine that we have the integral of sine of x squared times cos of x dx, and we're going from x equals 0 to x equals pi over 4. All right, well, what's our inner function? Well, it's a little bit harder to see, but if we think about sine squared of x is sine of x squared, we say, let's let u equal sine of x, and therefore du dx is cos of x, and du equals cos x dx. Well, making the substitution, we get the integral of u squared du. Significantly easier. But now let's also change our limits. So when x equals 0, going to my definition of u, when x equals 0, u equals sine of 0, which is 0. And when x equals pi over 4, u equals sine of pi over 4, which is root 2 over 2. So now we've re-expressed everything totally in terms of u. And when we do the integration, we're going to get 1/3 u cubed. We don't need to resubstitute it back in terms of sine and cosine because we've re-expressed everything in terms of u. So we're going to evaluate this function, 1/3 u cubed from 0 to root 2 over 2. So doing that work, we have 1/3 times root 2 over 2 cubed minus 1/3 0 cubed. And to simplify this even further, we get 1/3 times 2 to the 3/2 over 8. And while I can simplify that further, let's just leave it like that for now. So this is a huge difference between what we were doing before, because the key difference is we didn't have to resubstitute. We took our original limits of integration, which were in terms of x, re-express them in terms of u, and then we could just treat the entire thing as a function of u. Let's do one more example of that, and then let's end with a couple challenging problems. So let's, we can just even make up a problem. We're saying the integral, let's say x cubed plus 2x to the third, and what should go here? Try to figure out what should go there to make this a reasonable problem. Maybe pause the video. What should go there? If you guessed 3x squared plus 2, you're right, dx, and let's integrate it from 1 to 2. Okay, so steps. Find u. Let u equal x cubed plus 2x. Then what? Take the derivative and find du. This worked out nicely for us. Of course, because we made it work out nicely. So we can re-express this integral, but before we do that, let's change our x limits to u limits. So when x equals 2, u equals 2 cubed plus 2 times 2, which is 12. And when u equals 1, or sorry, when x equals 1, u equals 1 cubed plus 2 times 1, which is 3. Therefore, we can rewrite our entire integral in terms of u. So instead of x being 1, instead of going from x1 to x2, we're going to go from u equals 3 to u equals 12 of u cubed du. Doing the integration, we get 1/4 u to the 4th evaluated from 3 to 12. And we're going to get some huge numbers here. So let's just leave it as 1/4 times 12 to the 4th minus 1/4 times 3 to the 4th. And we'll just stop there. All right. Okay, so we've done definite integrals, indefinite integrals, and the next two problems are examples of really sort of tricky, challenging u substitutions. So turn your head on. Okay, so we're going to integrate, and we'll do an indefinite integral. We're going to integrate x times the square root of x minus 1. Okay, so dx. One thing that immediately pops out to me after having done these problems a lot, is I look at the inside and I want that to be the inner function, and then the outer function, well, this is not the derivative of the inside. So it's going to be a little bit different. But clearly, if we're going to make a substitution, we want to clean up the square root. That's the trickier thing that's going on. So we're going to say let u equal x minus 1. Done. Okay, so if u equals x minus 1, then du dx equals 1. So du equals dx. Cool. So what we could do is do our substitutions. But if we do our substitutions, what we get left is x times root u du. So we need to get x in terms of u. Well, going back to our initial substitution and solving it for x, we get that x equals u plus 1. So therefore, we can rewrite this as the integral of u plus 1 root u du. Now, while this may not jump out as immediately simpler, it in fact is, because if we distribute this, u times root u plus root u du, and then working with that to write it as u to the 3/2 plus u to the 1/2 du. This now is incredibly easier to integrate. So we've now can just use the power rule, and the power rule would make this u to the 5/2 plus u to the 3/2 plus c. And lastly, we're going to resubstitute. So we have 2/5 x minus 1 to the 5/2 and we have successfully integrated it thanks to our u substitution. Alrighty, here is our last problem, last example, and it's very similar to this challenge problem here. So our last problem, we're going to integrate x over root x minus 1. So very similar, and what I recommend you do is try to do this entirely on your own, and then by pausing the video and then unpausing it to see how you did. All right, so we want to clean up the inside, let u equal x minus 1, and if u equals x minus 1, du dx equals 1, du equals dx. So now I can get mostly substituted. That is u, dx is du. I just need to figure out what to do with my x, but it's going to be the same type of problem as the last one. We can write that u plus 1 equals x. Now we have it. So re-expressing this all in terms of u, we have the integral of u plus 1 over root u times du. Well, at this point, what we need to do is simplify rewrite this as two fractions, and that'll make this a lot clearer. So we have the integral of u over u to the 1/2, and I'm going to write u to the 1 just for the next step to make it clearer, plus 1 over u to the 1/2 du. And writing this as just powers, we have the integral of u to the 1/2 plus u to the negative 1/2 du. And now we're just going to use the power rule, or the reverse power rule. So this will equal 2/3 u to the 3/2 plus 2 u to the 1/2 plus c. And then we resubstitute. So our final answer is 2/3 x minus 1 to the 3/2 plus 2x minus 1 to the 1/2 plus c. So there ends our lesson on substitution, which is an incredibly helpful tool to enable us to find integrals of otherwise kind of complex and sticky integrals. Okay, goodbye.